Good morning. So, today we will start our discussion on pattern recognition problems, and today particularly we will talk about Bayes decision theory, which is the basis of statistical pattern recognition. Now, before I come to the pattern recognition problem, let us just have a quick recapitulation of what we have done over last 3 or 4 classes. Okay. So, over last few classes, what we have said is, given an object, we can find out different types of features of that object. The features may be derived from the boundary features, which are shape descriptors or shape features. Similarly, the features may also be derived from the region enclosed by the boundary, and those features can be, say, texture features, or they can be color features, they can be intensity features, and so on. We have also said that none of these features on its own can describe an object or a shape. Rather, many of the features taken together, they can describe an object to some degree of accuracy. Okay. So, instead of considering a single feature, we have to consider a feature vector where the components of this feature vector will be from different features, maybe from boundary features, maybe from shape features, maybe from region features like color, texture, and all that. They are to be concatenated in a particular order, and whichever order we concatenate them throughout our problem, that is modeling of the pattern as well as recognition of the pattern, we have to make use of the same order. So, when I put all these different features in a particular order, what I get a feature vector. So, the dimensionality of the feature vector will be dependent upon the kind of problem that we have. In some cases, maybe just 2 dimension is sufficient, in some cases 3 dimension, in some cases the dimensionality of the feature vector can be more than 100, maybe even 500 or so. So, as more and more dimensions or more and more features you add to the feature vector, the description becomes more and more unique. Okay. That is, to a great extent, the accuracy of the description increases as we increase the dimensionality of the feature vector. So, to what dimension of the feature vectors we have to go for in order to tackle a pattern recognition problem, that depends upon what is the problem that you have at hand, what is the complexity of the patterns that we have. Okay. Now, whatever it is, once we describe or once we represent a pattern by a pattern vector, by a feature vector, then this entire pattern is mapped to a single point in our feature space. Okay. So, if I have a 2-dimensional feature, then a pattern will be mapped to a point in the 2-dimensional feature space. If we have 3-dimensional feature vector for a pattern, then the pattern is mapped to a point in the 3-dimensional feature space. If we have n-dimensional feature vector, then the same pattern will be mapped to a point in our n-dimensional feature space. Okay. So, it is nothing but whenever we are finding out the feature vector, we are basically mapping that pattern to a point in the feature space. Okay. So, taking a very simple example, suppose we have 2-dimensional feature vectors. I am taking this example of 2-dimension illustration rather in 2-dimension, because I can very easily plot or demonstrate what happens in 2-dimension. Okay. As the dimensionality increases, the complexity also increases. So, I may not be able to plot them on a 2-dimensional plane. So, that is the only reason I am illustrating this with the help of 2-dimensional feature vectors. So, suppose my 2-dimensional feature vector has got 2 components, one is x 1 and other one is x 2. So, these are the 2 components of my feature vector. Okay. Now, different patterns will be mapped to different points in this 2-dimensional feature space. So, suppose I have got patterns belonging to 2 different categories. One of the category I may call as omega 1, that is one category, and the other category may be omega 2. Okay. Now, because I am taking patterns from these 2 categories, omega 1 and omega 2, so all the patterns which are taken from class omega 1, they will be put in, they will be mapped to a number of points in this two dimensional feature space, where the points will be very close to each other. Similarly, the patterns which are taken from this particular class omega 2, those will also be placed in points, mapped to points in this two dimensional feature space, where these 2 points will also be very close to each other. Whereas, the points corresponding to the patterns from class omega 1 and the points corresponding to the patterns from class omega 2, they are likely to be wide apart. Okay. So, effectively what I will have, for all the patterns which are taken from class omega 1, they will form a point cloud in this two dimensional space. Similarly, all the patterns which are taken from class omega 2, they will also be mapped to point clouds in this two dimensional feature space, where these two different clouds are likely to be wide apart if the patterns are widely apart. Okay. So, I will assume that all the points corresponding to the patterns in class omega 1, maybe they will be mapped to points like this. Okay. Similarly, all the patterns belonging to class omega 2, they may also be mapped to points or point clouds, something like this. Okay. So, this is the set of points which corresponding to feature vectors taken from class omega 1, okay, and this is the set of points representing feature vectors corresponding to the patterns taken from class omega 2. Okay. Now, in this simple kind of situation, this pattern recognition problem is nothing but something like this, that I have to find out a decision boundary. Okay. So, if the points lies on one side of the boundary, I will say that that point belong to one class. If it lies on the other side of the boundary, I will say that the pattern belongs to some other class. Okay. So, in this simple example, you find that I can draw a straight line separating these two different sets of point clouds. Okay. So, if I have an unknown pattern or the feature vector corresponding to an unknown pattern, and suppose the feature vector falls on this point somewhere over here. Okay. So, now since the feature vector is on the left side of this decision boundary, I will say that this feature vector belongs to class omega 1. If the feature vector happens to be somewhere over here, it is on the other side of the decision boundary, I will say the feature vector belongs to class omega 2. Okay. So, here designing of this classifier, okay, or training of the classifier means I have to find out the equation of this decision boundary from the set of training samples that are given to us. Okay. So, what are those training samples? This is the set of training samples taken from class omega 1, and this is the set of training samples marked in red taken from the another class, that is omega 2. So, both for these two sets of training samples, I already know what is their class belongingness. So, that is why this is called supervised learning. That means, for designing this classifier or for training of this classifier, I take a set of training samples for which the class belongingness is known. I take a number of training samples from class omega 1, I also take a number of samples from class omega 2, and making use of these two training samples, I have to find out this linear decision boundary. Okay. And because in this case the two classes can be separated by a linear boundary, this is also known as linearly separable classes. Okay. So, classes in this case are linearly separable. So, only when the classes are linearly separable, I can find out a straight line separating the two classes in 2 dimension. If it is in 3 dimension, that is I have 3 dimensional feature vectors, in that case I will have a plane separating the two classes. If the dimension is more than 3, I can neither have a line, a straight line, nor a plane, but what I have is a hyperplane. Okay. So, a hyperplane of dimension 4, hyperplane of dimension 5 in case of 5 dimensional feature vector, hyperplane of dimension 6 in case of 6 dimensional feature vector, hyperplane of dimension n in case of n dimensional feature vector. Okay. But in all these cases, the equation of the decision boundary, that will be linear. Okay. So, this is a very simple case where the classes are linearly separable. If the classes are not linearly separable, in that case what we do? So, let us take another illustration, say something like this. Again I have 2 dimensional feature vectors having components x 1 and x 2. Okay. I have so these are the samples which belong to class omega 1, that is one of the 2 classes. So, still I am taking the concept of supervised learning, that means for these samples I already know to which class these samples belong. Okay. Similarly, I have another set of training samples taken from class omega 2, which are distributed like this. So, I am putting these samples in red. Okay. So, find that I have this set of training samples which are taken from class omega 2. Okay. So, when the samples belonging to class omega 1 and the samples belonging to class omega 2, they are distributed like this. Now, you find that I cannot separate these 2 classes by straight line. Okay. Similarly, in 3 dimension, if the samples are distributed like this, I cannot separate the classes by plane, or in higher dimension, I cannot separate the classes by hyperplanes. Okay. So, in such cases, I have to have a nonlinear decision boundary, something like this. Okay. So, I have to have a nonlinear decision boundary. And we say that the classes are not linearly separable. Okay. So, among these nonlinear decision boundaries, the most popular one and the most common one is a quadratic classifier. Okay. Or at the most we can go for a cubic classifier. Classifiers of higher order more than quadratic or cubic is not very common, because designing such classifiers is not all that simple. Okay. Now, if I have a decision boundary as simple as this, possibly I can separate the boundaries by quadratic classifier or even a cubic classifier. But if the decision boundary is much more complicated than this, okay. Suppose I have decision boundary like this, something like this. Okay. So, you find that such boundaries, decision boundaries are so complicated, it is not very easy to design such decision boundaries analytically or to have an analytical expression for such a decision boundary. Okay. So, this is the case with when I am considering only a 2 class problem, that is I have only 2 classes omega 1 and omega 2. The decision boundary becomes much more complicated if the number of classes are more than 2. Okay. So, I can have 3 classes, I can have 4 classes, I can have 5 classes, I can have even 10, 15, 20 number of classes. So, as the number of classes goes on increasing and the boundaries are nonlinear, having analytical expression for such decision boundaries is almost impossible. Okay. So, the kind of approach that people take in such complicated cases is making use of neural network, where the decision boundary, the information of the decision boundary is actually encoded in the weight vectors or the weight matrices of a neural network. How many of you have done neural network course? Only 1, 2, 3, 4, 5, 6, 7. Okay. So, let us see, I mean, we will come to some neural network classifiers later on, but what does neural network do? So, this sort of decision boundary, though it is a complicated nonlinear decision boundary, but I can have a linear approximation of this decision boundary, something like this. Okay. A neural network in the simplest form actually tries to form a collection of such state line boundaries or piecewise state line boundaries, and that collection of state lines actually model a complicated decision boundary like this. Okay. So, what you have in a neural network? Let us see. A neural network has one input layer, one output layer, and none or more hidden layers. This is the output layer, and this is input layer. Okay. In every layer you have a number of neurons. Okay. So, here I can have one or more number of hidden layers, right. Now, in absence of any hidden layer, if I have just an input layer and an output layer, this is what is single layer perceptron. If I have hidden layers, within that I can have just one hidden layer, I can have 2 hidden layers, I can have 3 hidden layers, and so on. More and more hidden layers you incorporate, more and more complicated decision boundaries it can encode. Okay. So, if I have one or more hidden layers, it is called a multi-layer perceptron, multi-layer perceptron or MLP, right. Now, what you have is from each of the nodes of one layer, you have connections to every node of the upper layer. Okay. So, from every node in the input layer, I have connections to every node in the upper layer. So, it continues like this, and each of these connections have a connection weight. Similarly, from the ith layer to I plus first layer, every node has a connection. Similarly, over here from every node on this layer, I have connections to every node in the output layer. So, this way it continues, and each such connection has an associated weight with it, right. So, when I take any node in, let us say, J. So, let us call it a jth node, okay, and it gets connection from every node in the ith layer or every node in the previous layer. So, let us take a particular node, say ith node. To the jth node, okay, the total sum of inputs coming from the layers in the ith node will be given by Wij. This is the connection weight from the ith node to jth node, okay, times input to this, which let us say xi, okay, then summation of this over all I, because this node is getting the inputs from every node in the previous layer. So, this I corresponds to ith node in the previous layer. Okay. So, this is the total input to this jth node, right. Then you apply a nonlinear function over this f, okay, and this gives you the output of the jth node, which is Oj, right. Now, if I forget about this nonlinearity, what is the output of the jth node Oj? That is nothing but Wij times xj summation over all I, and you find that it is nothing but a linear equation. Okay. It is linear combination of all these inputs xi's. Okay. Similarly, for every j in this node, I will get a linear equation, right. Coming to the next layer, they are also feeding these inputs Oj to the nodes above it, which also combines them by a linear equation, and that continues till top up to this, right. So, finally, what I get is output of every node from the output layer is nothing but a linear combination of the inputs which are coming to the input nodes. And when you take the linear combination, the coefficients of this linear equation, they are different for different output nodes, which is nothing but a combination of the connection weights coming from all these different layers. So, effectively what I have is, I have a number of linear equations, okay, which are actually encoded within these weight vectors or weight matrices. Okay. So, more and more number of connections or weights I have within this network, more and more number of linear equations I can model, I can represent. So, as a result, such a kind of complicated boundary is actually modeled by a number of linear equations by such a simple kind of neural network, which is the multi-layer perceptron or MLP. So, we will come to details of this later on, and how this is related to some sort of analytical linear classifier that we can design following a criteria which is called a perceptron criteria. Okay. Now, you find that in all these cases, the decision boundaries are such that either the classes are linearly separable or the classes are non-linearly separable. Okay. Now, let us consider a situation something like this. Okay. So, you find that it is a spiral shaped object, and if I assume that all the points which are belonging to these gray shades, suppose this is the distribution of two dimensional feature vectors, right. So, if I assume that all the points which belong to these gray shades, they belong to class omega 1, okay, and the points belonging to the white region, they belong to class omega 2. Okay. So, here you find that the points are not coming as clusters of points, but the points are distributed following a structure, but the structure is so complicated that the points belonging to one class is totally intermixed with the points belonging to another class. Okay. Is it possible to have decision boundaries in such cases, so that the classification will still be successful? Okay. So, you find that neither linear classifier nor quadratic classifier nor even this simple multilayer perceptron that we have discussed just now will be able to give me, will be able to model a decision boundary which can classify the points belonging to two classes, which is the simplest problem, two class problem that we talk about in pattern recognition. Okay. So, I cannot have a decision boundary so easily if the points are distributed like this. Okay. So, one of the options that we can go in this particular case, suppose I define a number of rectangles like this. So, suppose this is one rectangle or boxes. Okay. This is another box, this is another box, this is another box, and so on. Similarly, for points belonging to the other class, I can also have a number of boxes like this. So, it continues like this. Okay. So, I actually mark these boxes as class omega 1, I mark these boxes as class omega 2. Okay. Now, once I have a box in 2 dimension or a hyperbox in n dimension, I can represent these boxes by something called mean point and max point, or whichever way I represent these boxes. Okay. So, what I actually have is I have multiple number of such boxes or multiple number of such hyperboxes. Now, if somehow I can collect these hyperboxes under the same umbrella. So, all these boxes B1, B2, B3, B4, they are put under the same umbrella named as omega 1. Right. Similarly, these boxes let me call as A1, A2, A3 and so on. These boxes I put under another umbrella named as omega 2. Okay. So, actually I have a collection of boxes put under two umbrellas. One umbrella is omega 1, other umbrella is omega 2. Right. Now, if I get an unknown pattern, suppose the unknown pattern is falling over here. If I have a representation of the box, I can easily find out in which of the boxes this unknown pattern is falling, this unknown feature vector is falling. Then I look at the umbrella under which this box belongs, okay? And accordingly I can say whether this unknown sample belongs to class omega 1 or it belongs to class omega 2. Okay. So, this is what is known as hyperbox, the classification based on hyperboxes. Okay. Such hyperboxes can also be represented by neural network, okay, in which case the neural network will represent these boxes in terms of 2 points, one is mean point, other one is max point. So, I can say this is a mean point, this is a max point, okay, because this is having the minimum x1, x2 feature values, this is having the maximum x1, x2 feature values. So, once I have this mean point and max point, it is something like left bottom corner and top right corner. If I have these two, then immediately I can draw a rectangle. I do not need any other information to draw a rectangle. Okay. So, if this box is represented by this mean point and this max point, it is what is called mean max classifier. Okay. On top of this, if I incorporate some idea of fuzzy set, this is what is called fuzzy mean max hyperboxes. Okay. So, if time permits, we will come to all these details later on. Okay. So far I have talked about all these different concepts just to tell you that what is the domain of pattern recognition problems and how complicated the pattern recognition problems can be, starting from the very simple linearly separable classes to non-linearly separable classes to classes which can neither be separated by linear boundary nor by simple nonlinear boundary. Rather, the classes will be represented as collection of chunks of data sets, okay, which have some class belongingness. Is that okay? So, these are the different problem domains or dimensions of the problem that we can deal with when we talk about pattern recognition. Okay. So, now let us come back to what I said that will be my topic of discussion today, that is Bayes decision theory. Okay. Now, to discuss about this Bayes decision theory, let me take a very simple example. The example is, suppose I have a manufacturing industry that manufactures machine parts. Okay. Now, you know that in any industry there is a section called quality control or quality inspection. Okay. What is the job of that particular section? They go for inspection of the products produced in that form. Okay. After inspection, if they find that the products are acceptable, they are meeting all the norms and specifications set for that particular product, it will be put under accepted category. If the product is not acceptable, there is some defect, it will be put under reject category. Okay. So, I was talking about two class problem. One class I said omega 1 and the other class I said omega 2. Okay. Here let me assume that this class omega 1 actually means the category accept, okay, and class omega 2 actually means category reject, right. So, when this quality control department, they will put an object under accept category or under reject category, they look at some of the features or something of that particular object to decide about this. Now, out of this, if I want to automate the process, let me assume that I want to form a decision rule to decide whether the object will be rejected or the object will be accepted. Okay. So, for that, suppose I want to go for the supervised learning mode. So, I have to take the previous history, that how many objects have been rejected and how many objects have been accepted by the quality control department. Okay. And based on that, I generate two probabilities. One is p omega 1, that is the probability that the object will be accepted or the probability that the object belongs to class omega 1, and the other probability is p omega 2, that is the probability that the object will be rejected or the probability that the object belongs to class omega 2. Okay. So, once I have these two probabilities, I can form a very simple decision rule. The decision rule can be something like this, that if probability of omega 1 is greater than probability of omega 2, then you decide in favor of omega 1. Okay. Or if probability of omega 1 is less than probability of omega 2, then you decide in favor of class omega 2. Okay. So, here you find that though we have been able to form a decision rule, but this decision rule is not really logical. The simple reason is, if from the history I have found out that p of omega 1 is greater than p of omega 2, then for all the new coming objects, I will always decide in favor of omega 1, even if it should actually belong to class omega 2. Or if p of omega 2 is greater than p of omega 1, I will always decide in favor of omega 2, p of omega 1 is less than p of omega 2, I will always decide in favor of omega 2 even if the class object may actually belong to class omega 1. That means, the objects will always be rejected or it will always be accepted based on our a priori probabilities p omega 1 and p omega 2. Okay. So, this is not at all a logical decision that we are taking. So, to make our decision more logical, what we have to do is, along with this a priori probability. So, these are called a priori probabilities. Okay. So, to make our decision more logical, along with this a priori probability, we have to combine some feature, let us say feature x. Okay. And in the simplest form, what this feature x can be? Suppose my decision whether the object will be accepted or whether the object will be rejected is based on the finishing or the polish given to that particular object. Okay. So, it is the quality of the polish, if I can quantize that or if I can measure that, okay, then that quality of polish can be represented by this variable x. Okay. It is good, very good, excellent, bad and so on. So, I can have different sorts of measure for this, and suppose it is measurable. Okay. Then that becomes my observation, and this observation is represented by this feature x, okay, where feature x can have various values. Okay. So, what I would like to do is, along with this a priori probabilities, I will also make use of this observation x or feature x to decide whether the object should belong to class omega 1 or the object should belong to class omega 2. Is that okay? So, again I go for the supervised learning mode, that means using some objects for which the decision has already been taken. So, I take some objects from class omega 1, that is the objects which are accepted, and I also take some samples of the objects from class omega 2, that is objects which are rejected. Okay. And I measure this feature x for those objects which belong to class omega 1, and I also measure the same x for the objects which belong to class omega 2. Okay. That means, I can find out a probabilistic measure or probability density function of variable x for the objects which belong to class omega 1. I can also find out the probability density function of the same observation x for the objects which belong to class omega 2. That is, I can find out what is p of x given omega 1. So, this is nothing but the probability density function of x taking the objects from class omega 1. I can also find out p of x by taking the objects from class omega 2. Okay. So, I can find out p x given omega 1, I can find out p x given omega 2. Okay. So, these are the probability density functions which are called class conditional probability density function. So, class conditional PDF, right. So, I have p of x given omega 1, I have p of x given omega 2. Now, my pattern recognition problem is, the decision problem is, for an unknown object I can measure x, okay, and from this measurement x, measurement of the feature x, I have to decide whether I should put this object in class omega 1 or I should put this object in class omega 2. That means, what I am interested in is, that is, my decision should be based on p of omega 1 given x, because I have this observation x, and based on that I have to take decision omega 1 or I have to take decision p of omega 2 given x, right. So, if I find that p of omega 1 given x is greater than p of omega 2 given x, then I will decide in favor of class omega 1. If p of omega 2 given x is greater than p of omega 1 given x, then I have to decide in favor of omega 2. And this decision appears to be more logical than our simplest decision that if the a priori probabilities are more, then I will put them in one class. And the more logical will be if this probability density functions, that is p of omega 1 given x or p of omega 2 given x, can be combined with a priori probabilities p of omega 1 and p of omega 2. Okay. So, if I can combine these two, then I will have a more logical decision rules. Okay. So, let us see that how we can combine these two. Now, from the preliminary probability theory, you know that the joint probability distribution, the joint probability density function, that is an object belongs to class say omega I. Let me generalize this, instead of calling omega 1 and omega 2, let me call it omega I can have a value 1 or 2. So, a joint probability that an object belongs to class omega I and at the same time have the feature x. Okay. This is not a class conditional probability, this is a joint probability. Okay. So, an object having is taken from class omega I and at the same time it will have the feature x. Okay. So, this joint probability density function is given by in terms of class conditional probability. This is nothing but p of omega I given x into probability of omega x into probability of x, p of x, or this is same as p of x given omega I into p of omega I. Is that okay? So, this joint probability can be written in terms of conditional probability, that p of omega I x, that is the joint probability that an object is taken from class omega I and at the same time it has a feature x, is nothing but p of omega I given x, that is the conditional probability, into p of x, and which is nothing but p of x given omega I into p of omega I. This is again a conditional probability and this is the a priori probability that we have already said. Okay. Now, from here you find that I get a very simple expression that p of omega I given x into p x is same as p of x given omega I into p of omega I. So, I get this expression from this preliminary probability theory. Okay. Now, from here what I get is, I already know what is p of omega I, that is a priori probability, based on what is the history of classification in that particular form, how many objects have been rejected, how many objects have been accepted out of the total number of objects that has been produced in that form. Okay. I take objects belonging to different classes, that means those objects which have been rejected, I also take those objects which have been accepted, and based on that I find out the class conditional probability density function of x, that is p of x given omega I. Okay. So, this p of x given omega I and p of omega I, they are known to me. For an unknown object, I measure the feature x, and what I have to find out is I have to find out p of omega I given x. Okay. Because then only I can say whether, or I will be able to say that whether this particular object having this feature x should be classified into omega 1 or it should be classified into omega 2, right. So, from here I get p of omega I given x is nothing but p of x given omega I into p of omega I upon p of x. Okay. So, from here I can have my decision rule. So, as I have P of, let me repeat this expression, omega I given x is nothing but P of x given omega I into P of omega I upon P of x, okay. Where what is this P of x? P of x is nothing but P of x given omega I, that is class conditional probability, into P of omega I. Take the summation, because I have got only two classes, omega 1 and omega 2. So, I is equal to 1 to 2. Is that okay? So, what I have is I have class conditional probability density functions of the feature x. I have a priori probability, that is P of omega I, okay. And using these two, I am computing P of omega I given x, okay, which is called a posteriori probability. Okay. Now, over here my simple decision rule. So, this is what is Bayes theory actually, right, and from this Bayes theory I can have simple Bayes decision rule, okay, which will be that if P of omega 1 given x is greater than P of omega 2 given x, then you decide in favor of class omega 1. Okay. Or if P of omega 1 given x is less than P of omega 2 given x, then you decide in favor of class omega 2. Okay. So, this is my simple decision rule, but when I perform this decision, when I take this decision, I make use of a posteriori probability, okay. And this a posteriori probability actually combines the class conditional probability and the a priori probability. Okay. So, I can make use of both, that is class conditional probability and the a priori probability to take this sort of decision. Okay. Now, here you find that over here my condition simply becomes, because P of x will appear at the denominator for both the classes omega 1 and omega 2. Okay. So, if I expand this expression, my expression will be P of x given omega 1 into P of omega 1. This is nothing but P of omega 1 given x. Okay. I am not taking into consideration P of x, because that appears in the denominator for both classes omega 1 and omega 2. So, this is my P of omega 1 given x. So, if this is greater than P of x given omega 2 into P of omega 2, okay, then I take decision in favor of class omega 1. That means, I say that this object belongs to class omega 1, right. So, over here if P of omega 1 is same as P of omega 2, that means, the particular form produces objects which are equally likely to be rejected or to be accepted. In that case, my decision is based on P of x of omega 1 and P of x of omega 2, that is class conditional probability. Okay. Whereas, if this is same, that means, for a given x, if belonging to class omega 1 or belonging to class omega 2, they are equal, okay, then my decision is based on the a priori probabilities P of omega 1 and P of omega 2. Okay. So, if I cannot take a decision based on the observation, I make use of a priori probability. Okay. If I cannot take a decision based on a priori probability, I make use of the observation. In other cases, you consider both to take your decision. Is that okay? So, this particular Bayes decision rule combines both your a priori probability and the class conditional probability to give you a decision rule which is more logical than simple rule based on your a priori probability only. Now, once we have this, what is the error that we will encounter? So, what is the probability of error or what is the total error that we will have in such cases? Okay. Now, let us see suppose this is my x and along the vertical axis I plot the posteriori probability p of omega I given x. Okay. And suppose the posteriori probability is something like this. This is for say omega 1, okay, that is p of omega 1 given x. Okay. Similarly, this is for omega 2, that is p of omega 2 given x. Is that okay? So, over here my decision rule was whenever p of omega 1 given x is greater than p of omega 2 given x, I decide in favor of class omega 1, and when p of omega 2 given x is greater than p omega given x, I decide in favor of class omega 2. Okay. So, my decision boundary is actually the point where p of omega 1 given x is same as p of omega 2 given x. Okay. So, this is my decision boundary where p of omega 1 given x is greater than p of omega 2 given x. Okay. But still you find that for a given x, if I decide in favor of omega 1, still there is a finite probability that the object may belong to class omega 2. Okay. Because here p of omega 2 given x is non-zero. If it was 0, then I would have said that there is no error, but there is a non-zero probability that the object may belong to class omega 2. So, there is a finite probability of error. And what is that probability of error? If I decide in favor of class omega 1, the probability of error is the probability that the object may belong to class omega 2. Whereas, if I decide in favor of class omega 2, then the probability of error is the probability that the object may belong to class omega 1. Okay. So, it is very simple that if I decide in favor of omega 1, then the error probability is p of omega 2 given x. Okay. Whereas, if I decide in favor of omega 2, then the probability of error is p of omega 1 given x. But whatever is the probability of error, that is the minimum possible error that I can have, is it not? Because if I decide for an object for which the value of x is here, say x 1, okay, over here p of omega 1 given x is less than p of omega 2 given x, but if I decide the object to belong to class omega 1, my probability of error is p of omega 2 given x, which is quite high. Whereas, if I decide in favor of omega 2, then the probability of error is p of omega 1 given x, which is less than p of omega 2 given x. So, whatever decision that we take based on a particular observation x, the Bayes decision rule ensures that the probability of error is minimized. Is that okay? So, given a situation like this, what is the total error that we can have? That is probability of error p error is nothing but the joint probability p error for a particular x into dx, where I have to take the integral from minus infinity to plus infinity, because over here you find that asymptotically the error value extends up to plus infinity on the positive side, extends up to minus infinity on the negative side. Okay. So, the total error P error will be given by the joint probability P error given x dx, take the integral from minus infinity to plus infinity, which is nothing but P error conditional on x, P error given x into P x dx, take the integral from minus infinity to plus infinity. Okay. And what is this P error given x? If I decide in favor of omega 1, this is P of omega 2 given x. If I decide in favor of omega 2, it is P of omega 1 given x. So, this P of error given x is nothing but minimum of P of omega 1 given x and P of omega 2 given x. So, for a particular value of x, whichever is minimum, whether it is P 1 given x or P omega 1 given x or P of omega 2 given x, whichever is minimum, P error given x is that only, because I am taking the decision in favor of the other class. Okay. So, let us stop here today.